Okay, so now that we've prepared the data, let's go ahead and start exploring it a little bit. And the first thing we want to do is take a look at a pair plot. So I'm just going to use the simplest form of this to start out with, which is sns.pairplot. So this is a Seaborn method. And then I'm going to specify the data frame, which is going to be the dummies. So we're going to start with the one that has the Boolean values. And that's all I'm going to specify. So let's go ahead and take a look at what we get. And this one can take a while depending on how many data points and how many columns you have. And what it's basically doing is it's brute forcing through every single pairwise combination of columns in the data set and sort of plotting a scatter plot for those two variables. Unless it's the same variable twice, in which case it by default just shows a histogram. So, for example, if we want to see how sepal length, which is the first column, compares with all these other things, that's the first column. So sepal length versus sepal width, you see there's kind of like two groups here that are kind of linear. And actually this has to do with the different species. So there's different relationships there. If you look at petal length versus sepal length or sepal width, once again you see sort of this cluster of dots where they're pretty much linear related, and then this other cluster down here where they're not correlated very heavily, and so on. And then generally, this is more than you need. So it's not only hard to read because it's a lot of information that's sort of densely packed, but it's including lots of stuff that I probably don't care about at this point. So do I really care that there's a high degree of correlation between the sepal length and the petal length? Well, maybe not. And if I do, it's something I can pull out and look at. What I really want to know, though, is how my independent variables like sepal length, sepal width, and so on correlate with my dependent variables, which are these Boolean things that are based on the species. So what I want to do here is sort of break those into two groups. So my x bars are my independent variables. And I'm just going to give a list of the names here. So sepal length and sepal width, petal length, and petal width. And then my dependent variables, the y bars, are going to be species setosa, species versicolor, and species virginica. Okay, and then if I execute that, I'm only going to get the pairwise combinations of these things over here with these things over there. And let's see what we got. So this first column is species setosa, and then let's look at the labels. So actually, this is not right. Oh, it is right. Okay. So species setosa, if you look at the first column, which is sepal length, you'll see that when sepal length is low, most of them are setosas. And when sepal length is high, most of them are not setosas. But there's sort of a overlap. There's blend. Same kind of thing here with sepal width. So wide sepals indicate setosa, narrow sepals indicate not setosa. But there's still overlap here in the middle. But then if you look at the next one, which is petal length, you'll see that, like, if you draw a line here, you'll see that pretty much everything where the petal length is less than that value is a setosa, and everything where the petal length is greater than that value is not a setosa. So this is a really excellent way of classifying whether something's a setosa or not, just looking at the petal length. And then petal width also works quite well for classifying whether it's a setosa or not. For versicolor, you'll see that all of the versicolors are sort of in the middle of the range for sepal length, and so there's ones that are not versicolors on sort of the whole spectrum here. So these are really hard to separate out based on sepal length. Sepal width is a little bit better. There are some down on this end that are versicolors, but by and large, lots of them have all sorts of different values. When you get to petal length, though, you see what's really going on. So what's really going on is that these are setosas here on this side, and then these are virginicas over here, and the versicolors are sort of in the middle. So you can look at this and sort of see what's going on, but if you think in terms of a linear regression, if you were going to plot a line, what you really want is higher values of that line indicate versicolor and lower values of that line indicate not versicolor. And this is just not a linear relationship. So no linear regression is actually going to fit this curve particularly well. And then same thing here with petal width. So basically the answer is none of our inputs are very good, will be very good at predicting whether something's a versicolor or not. However, we can do a really good job at classifying setosas. And if we look at virginicas, we also see that, well, most of the ones with long sepals are virginicas, and sepal width is not particularly good. But petal length, the really high petal lengths are mostly virginicas, and petal width, the real high petal widths, are mostly virginicas as well. So what this tells us is that we can do a pretty good job of building classifiers for is a setosa and for is a virginica, but we can't really build a good classifier using a linear regression model for is versicolor. And let's actually see how that plays out. So let's go and look at correlation and see what that tells us. So we sort of did a deep dive looking at the actual values. Let's just look at some raw correlations and see what we can tell from that. So if you take a data frame like iris data, there's a core method on it which just gives you a correlation, correlation numbers, and actually I wanted to do dummies, sorry. So this is showing me for each pair of columns how well they correlate with each other. And so sepal length and sepal length correlate perfectly, sepal width and sepal width correlate perfectly, and so on. So along this diagonal, everything always correlates perfectly with itself, and so 1 is the maximum value of correlation, and that's what you get there. But then high numbers, numbers close to 1, indicate a really high degree of correlation. So for example, petal length and sepal length are very highly correlated. And then very low numbers, numbers close to -1, are inversely correlated. So for example, if you look at species setosa, longer sepal lengths are negatively correlated with species setosa, which basically in English means that the longer the sepal is, the less likely it is that something's going to be a setosa. And the magnitude of this number is important. So really big negative numbers and really big positive numbers are both great for doing prediction. The ones that aren't very useful are the ones that are sort of in the middle, like this 0.2, that's a fairly weak correlation. So this says that petal length is not highly correlated with versicolor, and so petal length is not a particularly good predictor of versicolor. And petal width is even worse. So 0.11, that's almost 0, and 0 means there's no correlation at all. So What this tells us is that petal length and petal width are not good predictors of versicolor for the same reason as we saw up here when we were looking at the scatter plots, because versicolor is right in the middle here, and some of them that aren't versicolor are low and some of them that aren't versicolor are high. But of course we know, the program doesn't know because it's just statistics in the program, but we know that the reason that we're seeing this relationship is because all the setosas are down at this end and all the virginicas are up at that end. So we can actually use some knowledge to get a better model out of this thing than the raw statistics are going to generate for us. Now, this has all the information we need, but it's not necessarily visualized in a way that it makes it easy to tell what's going on. And so one thing that's really common to do is to use a heat map where you're coloring the background of each of these cells in order to draw attention to the ones that have the highest correlation or negative correlation. And then you can do that. That's a Seaborn function as well. So seaborn.heatmap. And then you just pass it this correlation matrix. And what it does is it gives you a scale from -1, which is the strongest possible negative correlation, up to +1, the strongest possible positive correlation, and then 0 is sort of in the middle. And so like this thing here, this is really close to 0. And so this means that petal width is a bad predictor of species versicolor. On the other hand, these light ones up here, so for example, like, actually I'm going to go to the other end. So sepal length, petal length, and petal width are all very strong anti-predictors of setosa. So if you see high petal widths or sepal widths and so on, that means it's not a setosa. And then petal width is positively correlated with virginica. So bigger petal length and bigger petal width are good indicators of virginica. Now, I also prefer viewing it this way. So I like adding this annote, which actually shows me the degree of correlation right on each box. And then this is maybe not the most useful coloring scheme for me. So like the book likes this blue one, like so. And here, this is a little easier for me to tell at a glance what's going on. So I'm looking for the white ones, and those are the negative, strong negative correlations are white. And then the dark ones that aren't on this diagonal, these are the strong positive correlations. So you can tell at a glance that petal width and petal length are highly correlated. If you just focus on this half of it, you're looking for petal width and petal length and sepal length are all highly positively correlated with virginica. And then sepal width is highly positively correlated with setosa. Petal length and petal width are highly negatively correlated, and sepal length are negatively correlated with setosa. And then sepal length is, these are all sort of in the middle. These are probably the best predictors. Are sepal width is a negative predictor of versicolor, but it's not as good as most of these other predictors, which are, so like these are 0.89 as a predictor, 0.7, I'm sorry, 0.6, 0.72, 0.77, minus 0.89, minus 0.92. These are all pretty good predictors. There aren't any great predictors for versicolor by itself.